this as a 3-port network, a 3-port component. Okay, so you need to have a 3x3 matrix. So this one is out. Okay, so the only one that is available is this. So the answer is this one here. Right. So just to recap, in the lecture, okay, I've shown you this particular during the lecture as well as during the tutorial. I've shown you that the ABCD matrix of a transmission line of length D is this. Okay, so if this is a quarter wavelength, then this one will be 1. Okay, cos beta D, cos pi over 2 will be 0. Sin pi over 2 will be 1. So this will be JZ0. This one here, sin pi over 2 will be 1. So this will be 1. And this one, cos pi over 2 will be 0. Okay, so for quarter wavelength transformer, this is your ABCD matrix. Right, so the answer for 3 is C. Right, so for this particular SFG, okay, we're supposed to observe how many first order loops there are. Right, so in this case, here is a loop. Right, here there's another loop. Okay, so this is a first order loop, this is another first order loop. So the answer for question 4 is 2. Okay, so the answer for question 4 is 2. There are 2 first order loops. Right, the next question is how many second order loops are there? Okay, how many second order loops are there? Now, we've already seen that this has 2 first order loops. One here, another here. Right? These 2 first order loops do not touch each other, hence that form a second order loop. Okay, so for 5, the answer is B. There is 1 second order loop. Right, so for this one here, straight away you should be able to deduce that this and this are inadmissible. Okay, this and this are inadmissible because the denominator is D. Okay, so if you want B over D, you must find a path that goes from D to B. Okay? If you want D over B, you must find a path from D to B. But if you look at D, there is no path that allows you to go outwards. Okay? Over here, the path stops. And over here, if you follow this one here, the path also stops. Okay? So we cannot go from D to any of the other nodes. Okay? This D here will not allow you to go to C, will not allow you to go to A, and will not allow you to go to B. Okay, so meaning that's A over D, B over D, and C over D, they're all not possible. Okay, right? So coming back to here, right? From deduction alone, or from observation alone, this and this are not possible. Okay? The only 2 possibilities is either this or this. Okay? So the question is, let's try one of them. Let's try B over A. Right, for B over A, first of all, you need the denominator. Okay, the denominator requires you to look at this first order loop and this first order loop. Okay, so the denominator is 1 minus, this is 2 times 2, that's 4. And this is again 2 times 2, that's another 4. Alright, so this one is 1 minus sum of all first order loops. Then add sum of all second order loops. Okay, there's only one second order loop, which is the multiplication of these two. Okay, so this is 4, so it's 16. So denominator is, from here, the denominator is 9. Okay, the numerator, well, the path from A to B is this. Right, that's the path from A to B. So the numerator is 1 minus all first order loops that do not touch the path B. Okay, this red loop touches the blue path, hence this loop is to be disregarded. This red loop does not touch the blue path, so this one has to be included. Okay, so 1 minus 4. Right? How about second order loops? Well, this one touches, so there are no second order loops that do not touch the blue path. Okay, so it's 0. Right? So the numerator is minus 3, and therefore you have minus 1/3. Okay, so B over A is minus 1/3. And question 6, the answer is A. Now question 6, another possibility is C over A. Okay, let's check C over A. Right, now I want C over A. Okay, for C over A, the path is no longer this blue path. Okay, so from A, you want to go to C. Well, it is this path here, as well as this path here. Right? So for this, we find that if I take this path first, it is 1. Okay, minus all paths, all first order loops that do not touch the green path. This touches, so this is the only one that's left. Right? And then this one here, okay, plus 3.
1 minus 4.
Oh yeah, 1 minus 4, sorry. Okay, so this second path is 3. This and this do not touch, so it's 1 minus 4 minus 4. Okay, and these two form a second order loop, and it does not touch the green path, so it's plus 16. Okay, so if you work it out, you find that it is not equals to minus 1/3. Right? So question option C is wrong. Okay? Right? So option C here is incorrect. Right, so this question 7. Okay, we're talking about this WR51 waveguide. It has cross-sectional dimensions given like that. Okay, right. The T1 knots mode is the dominant mode. This one, it is obvious. All waveguides have the T1 knot mode as a dominant mode. Okay, the word dominant is a technical term. It means the first mode that is in operation, the main mode. Okay, so this one is true for all waveguides, not just the WR51. Then this one here, the T2 knot and T knot 1 have the same cutoff frequencies. Okay, so the cutoff frequency is given by C over 2A for T right, so now this one you want to, okay, so for T2 knot, okay, this one here is like so, right? Now, if you look at these dimensions here, A is equals to 2B. Okay? Over here, A is equals to 2B. So you substitute this into here, you find that the two of them will have the same cutoff waveguides. So this is true. Okay? Then 15 gigahertz signal will be able to propagate through this waveguide. Well, let's go back to your dominant mode. For T1 knots, this is your dominant mode cutoff frequency. Okay, so if you put in the numbers, if you put in the numbers, 3 times 10 to the 8 divided by 2 times A is 0.013. Okay, you will have 11.5 gigahertz. Right? So if the waveguide has a cutoff frequency of 11.5 gigahertz, then a 15 gigahertz signal will certainly be able to propagate through the waveguide. Okay, so this part is also true. Right? So the only one that is untrue must be this one here. This one here must be untrue. Okay? Why? Well, this is kind of like a trick question. I've actually mentioned to you during the lecture, there is no TM10 mode or okay, there is no TM-M0 mode nor TM0N mode. Okay, for the TM, for the transverse magnetic case, your surfaces, okay, cannot be 0. Okay, so in this case, this one here, this mode is non-existent. Okay, so this is a bit of a trick question. You must be able to spot that this particular mode here does not exist. So 7, it is C. Any questions thus far? This one here? The TM mode, I've explained during lecture that this TM mode here does not exist for when one of the two surfaces is 0. Okay, let me grab hold of the lecture page. Okay, now these are the electric fields and magnetic fields for the TM mode, right? Now, what if M is 0? If M is 0, then this one drops to 0 because there's an M there. Sin 0, this will drop to 0. Sin M, this will drop to 0. And over here, you have an M, this will drop to 0. Okay, so M cannot be 0. Same for N. If N is 0, sin N here will drop to 0. Okay, over here you have N, so that will drop to 0. Over here you have N, that will drop to 0. And over here, sin N here will drop to 0. Okay, so neither M can be 0 nor N can be 0 for a TM mode. Right? So when I ask you about, okay, so this statement here is invalid because there's no such thing as a TM one-knot mode. Okay? So far, have you all been getting the answers correct? Because I see that none of you all seems to object to any of the answers. Okay? If you feel that your answer is correct, please voice your objection so we can discuss about it. Right, so an engineer plans to design a rectangular waveguide cavity. Okay? Right, he wants it to operate at 10 gigahertz. Okay, so the first consideration is that your rectangular waveguide must be able to support it. Okay, right. The color frequency for the TE1 knot mode is given by this. Okay, so what we have then is we apply this formula. Okay, you apply this formula to all of these here, and we get hold of the cutoff frequency. Okay, so this one, the cutoff frequency is 11.5 gigahertz. Right? If the cutoff frequency is 11.5 gigahertz and this one wants to operate 10 gigahertz, so this is out of question. Okay? Because it will not allow a this will not allow a 10 gigahertz signal to pass through it. Okay? The second one, this is 6.6 gigahertz. Okay? So this is a possibility. Okay, in fact, this is the answer. Right, the next one, FC is 4.3 gigahertz. Right, now, if FC is 4.3 gigahertz and this is for TE1 knot, then FC will be 8.6 gigahertz for TE2 knot. Okay, so that means that when you want to operate your waveguide cavity at 10 gigahertz, okay, you only want it to operate at the dominant mode, right? But this one here, we find that the next mode is cropping up. Okay, the next mode can propagate as well, right? So for this one here, 4.3 gigahertz is too low, so this is not acceptable. Okay, and finally for the last one, is 3.7 gigahertz. Okay, so this one is unacceptable for the same reason as this one. Okay, this is too low. It will allow the TE2 knot mode to propagate at 10 gigahertz. Right, so this one is also unacceptable. Okay, so for question 8, the answer is B. Yeah.
For our lecture note, inside our lecture, this table,
Mm-hmm.
we cannot use the formula.
What table?
This kind of table for all the.
Okay, we're talking about the WR table, is it?
Yeah. If you go through the WR, the next page, WR 51,
Yep.
how you go and calculate the FC?
Right, so WR 51 is here. Okay.
And the dimension, the A is 0.510.
This is in inch.
Oh.
No, it's written as in inches. Okay. I told you during the class that in industry, the convention is to cite all this in inches. Okay. And because of that, this 5.1 is borrowed to over here. WR 5.1. Okay, it's because it is 0.51 inch. Okay, so it's cited in inches. That's why the WR here is all, the number here is in inches. Okay, so if you convert this to millimeters, then you get it correct, right? Anyway, since we're on this page, okay, so WR 51, we find that this is not possible. Okay, this one here is, this is the recommended range, and 10 gigahertz does not appear inside your recommended range. Okay, and for WR 137, this is the recommended range. Okay, your 10 gigahertz is outside the recommended range, right?
So in future, if inside if the exam, at the examination, they give you another A, we cannot just remember the function range, right? We need to calculate ourselves.
You mean the recommended range?
Yeah.
Yeah, you have to calculate it
If
yourself.
they change another A, maybe the FC different, maybe the FL and FU.
Correct, yeah, you have to calculate your own. Okay, and in the exam, I'll always give it to you in millimeters. I mean, this one is industry practice. They cite it in inches. I can't help that. This is what industry does. Okay, but in the exam, I can help. I'm in control of it, so I will give you the A and B values in millimeters rather than in inches. Okay, right? Then the other one is WR159. Okay, so this is the recommended range, and again, 10 gigahertz is outside that range, right? So that's why question 8 the answer is WR90. WR90 is here. Okay, so 10 gigahertz is right in the middle of the range, recommended range, and therefore this is the most suitable. Okay? Right, so having considered the choice of waveguide, okay, so the choice of waveguide is the WR90, and A and B are known. Okay, so now the question is the length of the cavity. Okay, so you have chosen the WR90, or at least I hope you have chosen the WR90. Okay, so A and B are now known. Question now is L, right? Now you want this to operate at 10 gigahertz. Okay, so you have to use the formula. The formula is okay, this is the formula for the resonance frequency. Okay, this one is of course for TEMNN. Right? But in this case, we want to operate it at TE101. Okay, so for TE101, your M, set it to 1. Okay, this one is 0. Okay, for T. Right, your M is 1, your N is 0, and your P is 1. Okay, so this is the formula that we have to use. Okay, so you substitute 10 gigahertz into here. A is known. Okay, it's given in the previous question. L is now the one that you have to obtain. And when you calculate it, it comes out to be 20 millimeters. Okay, so question 9 is C.
Sir, how do I know it's operated on TE101?
That's the dominant mode.
Dominant mode for this one.
Yeah, it's always operated in the TE101. Okay, the TE101 is the one with the lowest resonance frequency. All the other numbers for M, N, P, all the other numbers will give you higher resonance frequency. Okay. Right, so finally, question 10. Right, question 10 is like this. Okay, so looking at it, we see that there is symmetry here. Right, so obviously a signal. Oh yeah. Right. So you have symmetry about here. A signal coming in here. Okay. It will be reflected by, let's say, gamma. Okay, 1, right? Now, because of symmetry, over this side, a signal that comes in here will also be reflected by gamma. Okay? But a signal coming here, we cannot deduce that this one will reflect back by gamma. Okay? Over on this side, what is reflected back, we cannot deduce. Okay? Or rather, we cannot infer that it is equal to this and this. Okay, so these parts here, S11 and S22 are equal. This is correct. But S33 being equal to these two, that one is uncertain. Okay, so this here is inadmissible because all 3 diagonal entries is gamma, small gamma. This one also. Okay, so this is out. This is out. The only possibility are these two. Okay. Okay, so here you find that these two are equal, but this one is another term because we cannot deduce that this is equal to these two. Okay? Right, so let me write the sketching matrix. Okay? So this is S22 and S33. We can deduce the S22 and S33 must be equal to each other. Okay? But S11, we don't know what it is, so let's call it big gamma. Whereas Z2, let's call it small gamma. Okay? Now, right, a signal coming in here, it will be split equally here and here, okay, by symmetry, right? If I have a signal coming in here, it will split equally here and here. So if I call this alpha, okay, So S21 is alpha, S21 is this, S31 is alpha. Okay? By reciprocity, right? Because I did not mention that it contains ferrites, crystals or plasmas. So by reciprocity, S12 must be equal to alpha. And by reciprocity, S13 must be equal to S31, alpha. Okay? Now, the final one is a signal. A signal coming in here and coming out here. Right? This part we cannot infer that is equal to anything else. Okay? This one here we cannot infer that it's equal to anything else. Let's call this beta. Okay? So over here, this that is S23. S23 is beta. And by reciprocity, S32 is also beta. Okay? So conclusion, the answer is this one here. Right? So question 10, the answer is D. Sorry, not this one. Not this one. Below. Okay? Right, any questions? Any questions?
The last one, the beta, how come it's beta?
It could be anything. Let's just call it beta. You cannot deduce that this term here must be equal to alpha, gamma, or big gamma. That's why I give it another symbol. Okay? If you don't like the symbol gamma, you can call it tau. Right? You can always call it tau. Right? If you call it tau, then I come over here and change it to tau. Okay? Any other questions? No? Okay, it's coming to 7 o'clock already, so let's go for a dinner break and then we come back and resume our lecture.